Hi everyone, and welcome to Erik's Electronics Workbench, and part 2 of the Fluke 8125A digital multimeter repair. Now if you haven't seen part 1, definitely check out that video. It'll bring you up to speed on where I'm at in this project, and I'll post a link to that video in the description below. Alright, so let's continue. All the electrolytic capacitors have been ordered, so while I'm waiting for them to arrive, there's a number of other repairs that I can make on the multimeter. Now my thought for the troubleshooting is to replace all the electrolytic capacitors, and if by chance that solves the problem with the ring counter circuit, then great, we'll move on. But if not, then I'll revisit doing the troubleshooting in this ring counter circuit. Now, as you saw in part 1, there's an electrolytic capacitor right here that had excessive leakage current when I removed it and did that leakage test with my Sencor capacitor tester. And I'm sure that the other electrolytic capacitors are probably in a similar state of condition, just given that here in 2025 this instrument is nearly 50 years old. So even if replacing all the electrolytic capacitors doesn't solve the problem in the ring counter circuit, it'll still be a good idea just for the reliability of the instrument. So some of the other repairs that I can make are more mechanical in nature. So I noticed that the instrument was either dropped or handled very roughly, and I mentioned that in part 1. There was a very noticeable bend on this panel right here in this back corner, and I straightened that out already. I used a press and was able to press it back into position. I didn't need to remove these channels from the rest of the instrument. This side panel and this panel are riveted to this back panel. Rivets in the corner right there, and the rivets are in good shape. They're tight, no problems there. But it saved a lot of work not having to remove all of this from the instrument. So I was able to turn the instrument on its side, block it appropriately, and then be able to press that down. There was just enough room to get in past that transformer and squeeze this back flat. Something like this, you never want to hit it with a hammer to try and straighten it out. There was also a dent, I don't know what happened on this corner right here, but it was kind of rolled up a little bit, and I straightened that back out and filed it smooth, so that turned out very nice. This was bowed in considerably in the back right here, so I straightened that out. The transformer was loose on its mounting screws, so that's been tightened up. On the front panel, I still need to remove the entire front panel assembly. If I turn the instrument here, so on this front panel, these buttons are behind this rubber, sort of an overlay that's on the buttons, which makes them waterproof. And the rubber is not installed correctly. On the back of the panel, it's completely out of position in most of the locations. So the only way to repair that is to remove this whole front panel. So that'll be a little bit of work to do, but not impossible, of course. So I'll get started on doing that. These fuse holders are broken. I have new fuse holders on order. They're not here yet, but I'll remove these and get it prepared to install the new fuse holders. So a number of other just minor things that can be taken care of on this corner back here. And this again on this back corner, or front corner I should say, right here. There's some damage to the metal. This piece right here where it attaches to the side panel, there's 2 screws that come in here. The metal has been damaged right there. Again, extremely rough handling, I would think, because I don't know how else you would ever damage that. In normal use, it would never get damaged. So I'll take care of that as well. And this will come apart when the front panel is removed. I'll be able to have access to this corner and deal with those pieces. They're basically threaded inserts that have come loose right here, and the metal has some damage, so I'll have to take a closer look and see what needs to be done there. And this piece right here is the shield and the support that goes behind the Nixie tubes. So you can see the Nixie tubes right there. So this piece fits right in behind here, like so. And this little area right here that kind of comes out like a little box right there, that just supports the back of this meter that's right here, which is the battery meter or the line voltage meter. Now on this piece right here, there's actually a part that's broken off right on the side. I'm not going to worry about that. There's actually a piece completely missing, and then the other piece is still attached to the panel right here. But this will be installed with 2 screws across this area, and that'll be perfectly fine. This piece that sticks off over here is still rigid enough. There's enough plastic right here that it'll just sit there, and it's not a problem. The meter's not going to fall out of position. So this corner right here has been broken out, so it needs some repair to that plastic. You can see right there. So my thought is to use this very small little standoff piece right here. Oh, get that back in there so you can see it. I'll bring it up a little closer. This little metal standoff. I'm going to use some epoxy and try to epoxy that into position to build up that corner. So I'll show you that when it's done and how that works out. Again, if I just bring this up a little bit closer here, you can see, oops, touched up there. That piece is kind of broken out right there. It's basically something is missing. There's a chunk that's missing out of this corner. And there's supposed to be a screw that goes through here and goes down to the circuit board. So this, of course, sits this direction. So the one that's in the middle right here is perfectly fine. No problems with the plastic here. So I'll continue on with that repair as well. All right, so I now have the front panel disassembled. The components that you see remaining didn't need to be removed. This is all related to AC wiring and the heater circuits. These are thermal switches right here. So it was a fair amount of work to get the panel to this point, but the reason I had to disassemble the whole front panel is because there was damage to a number of different pieces on this panel. So the fuse holders I already mentioned were broken. I talked about that in the part 1 video. You can see this fuse holder is just completely destroyed. It looks worse now after it was removed because just in trying to remove it ended up making it kind of break open further. So I took the fuse out and the cap that's under this metal cap right here. Nothing wrong with those pieces, so I saved them. So again, I have new fuse holders on order, and they contain this weather-tight cap that goes on the front, so exact replacements. So both fuse holders were damaged basically in the same way. And there was a nut on the back side right here, and it had an adhesive glue, or almost like an epoxy, holding them in place, basically for vibration proofing it. And that glue was incredibly strong, so I had to chip just bit by bit and break that glue out of there, but that's all been cleaned up as well. So another problem was that on the buttons right here, so you see this side when it's all assembled, this is a rubberized piece right here, and then there's actually plastic buttons that are embedded into the rubber, and then those plastic buttons, of course, attached to these shafts that are on the switches right here. So this was not installed correctly. Luckily, none of the rubber is torn. You can see it's folded a little bit awkward right there, and this corner is pinched down just a little bit, but there's actually no serious damage. So this will easily reinstall correctly into this area right here. You can see it's been cut out and sort of machined down. So this rubber piece fits in here like so, and then this ring right here fits on the back side like this, and then from the front side screws go through, and there's threaded holes that are in this ring, so it just holds everything together, and it makes this a watertight fit on everything. Now, if you ever have to disassemble one of these, it appears to be that the right way to take it apart is to take these plastic buttons and pull them off of these switch shafts. They sort of click into position. There's just a little, like a piece inside that kind of snaps down into a little groove right here. So if you take a screwdriver and just very carefully get between the button and the end of the shaft right here and just kind of push on it a little bit, these came loose. But I didn't know that at first. I was trying to pull these plastic buttons out of this rubber, and this one in the middle did come out. And if you take a look right here, I'm going to zoom this in. Very unusual design. So you see on the 4 corners, see those edges that are lifted up to those sharp points right there? So all 4 corners have that. So it essentially, they're very sharp on the edges, but it makes these buttons grab into that rubber piece, sort of like a one-way fit. So you can see how those corners come out right there. So of course this is the front of the button right there. The back side right there is where it goes onto the switch shaft. So basically when these go into that rubber, it's a one-way fit. They push in, but they won't come back out. So if you try and pull them back out, these very sharp corners will end up ripping the rubber. And luckily there is no damage to this piece right here. You can see a little bit closer right there. So that one button will go back in here, but there's nothing is torn on these buttons. Everything is in good condition on this rubber piece. But it wasn't installed correctly at all. You can see it's been pinched right there, but this will lay back down flat under that rectangular shaped piece that fits over it. The screws will hold it in place. So this will all reassemble very easily. And then once this is in place, the main switch shafts right here need to be aligned and push up into this all at the same time. So a little bit tricky, I suppose, to put that all back together. We'll have to see how that works out. But anyway, that's going to be reassembled in here, and you have to have this front removed like this to get into the switch assembly and install it correctly. Now another area of damage was this front piece right here. So this fits just like so, and there are 4 screws that come in from the front, attach that into place, and then these sides right here have these captive nuts or threaded inserts that are pressed into the aluminum on the sides, and that's where these side rails attach onto this front piece. And on this side right here, this was all pulled apart. The metal was actually ripped right there. I don't know how someone would have put that kind of force onto this and, you know, pulled it apart basically. Very strange. This side had a slight bend, but it wasn't too serious. So I straightened this out and have repaired this side over here. So get this zoomed in a little bit closer for you here. You can see I straightened the side. The paint has a few scuffs in it, but you won't see it. It's not visible when it's all assembled, so I'm not worried about that. You can see a few marks right here where I had to press this back flat. I just used a hydraulic press to squeeze that. Some small blocks of metal to press in the right places. This other side over here, again, a few scuffs on the paint, but nothing too serious. So I think it turned out very well, and mechanically this will be strong again, and it will go together the way that it's supposed to. So I'm happy how that turned out. And this piece right here is the holder for the Nixie tubes. So it installs like this, and the Nixie tubes fit up into here, and the tops of the Nixie tubes poke through those little holes. And the meter that's on the front fits into this area over here. And I already mentioned there's a part that's actually broken off over here. I'm not worried about that. I'm not going to do anything with it because there are two places that this is actually going to be held, right here and then right over here. So this will be very secure. However, this corner was broken out, and you can see, I'll bring this up a little bit closer again. So turn it over this way. So you can see that new piece right there, that sort of a round, it's basically a standoff. And I'll make sure this is completely in focus here. So I'll put up on the screen a couple shots as I was doing the repair. You can see how that looked. I used a 2-part epoxy. And what I did is I put this plastic piece in position first. I set the little round standoff in place where I wanted it. A little piece of the plastic right here came down next to the side. I had to grind or file down a little spot on the side of that round insert so that it fit correctly. And then I put just one drop of super glue to hold it in place. And when that cured, I took this out, but that held this standoff, which forms the hole right there where the screw will go through. It held it in the right place, and then I built this up with the 2-part epoxy. So I think it turned out very nicely, and this round shape that this has is basically identical to this round shape that the other one has. So basically looks the same. So I think that turned out very nicely. Just a little bit of black paint on there, it makes it all blend together. So again, mechanically, this will be strong and it will hold that corner the way that it's supposed to. So my fuse holders are not here yet. So I'll go ahead and wait, until the fuse holders get here before I can reassemble this whole thing back into the instrument. But I can put a few of these components back in place, like the rubber piece for the switches and the other bracket that goes up in the front here. Something else just to note is if you have to disassemble one of these instruments, these are the 3 binding posts for the test leads on the front panel. And there's a circuit board that fits right here, and it looks like the best way to take it apart is to just take the 3 nuts off of here and then leave the circuit board in place in this corner. And when the 3 nuts are off, when you remove the front panel away from the instrument, then the circuit board stays there, and these studs just move and come back out of the circuit board. Because the other way is to desolder the wires on that circuit board, which looked to be a lot of work. However, one of these nuts is very, very difficult to reach. I had to use some needle nose pliers to get into it, but ultimately, it worked out okay. So this looks like it's probably the best way to disassemble this. The new fuse holders have arrived, as well as all the electrolytic capacitors, so it's time to start installing components. So I'm going to start with the fuse holders and reassemble the front panel, and then I'll move on to the capacitors. Now in this mix of capacitors, there's actually 2 tantalum capacitors, and because of the types that are used, they look very similar to the electrolytic capacitors, and I'll show you in just a moment how to spot the difference on these tantalum capacitors. Now you may have seen tantalum capacitors that look like a little droplet style, and they're often yellow in color, and those are radial leaded type capacitors. Again, very easy to spot that design, but these are all axial leaded capacitors, and the tantalums and the electrolytics do look very, very similar. Now, tantalum capacitors are generally quite reliable unless they're subject to an overvoltage condition, but they're not prone to the same types of failures as electrolytic capacitors. But because the instrument is all taken apart, and given the age of this instrument, I thought it would be a good idea to replace the 2 tantalum capacitors that are in this instrument. And luckily there's only 2 of them because they're quite expensive, considerably more expensive than electrolytic capacitors. So again, I'm glad there's only 2 to replace. So this is one of the tantalums right here. So you can see the electrical specs right there. But the way that they're very easy to tell that this is a tantalum and not an electrolytic is if you look at the housing on the end right here, these tantalum capacitors have a little tube that sticks out where the wire lead is attached. And then that wire lead is either welded or soldered onto the little tube. And then also in the end right there you can see there's like a glass or maybe an epoxy type seal, so it's hermetically sealed. So those features are unique to these tantalum capacitors. You wouldn't find an electrolytic that has that same design on the end. So it's particularly that little tube that sticks out. Now the other end of the capacitor looks very similar to an electrolytic, the way that the wire lead is just welded to the housing. All right, so again, very important to know the difference because if there's a tantalum capacitor, you should replace it with a tantalum and not an electrolytic. Also, don't confuse this type of capacitor that has that little tube sticking out of the end where the wire lead is attached. Don't confuse it with a very old style paper and oil capacitor. Very early types of capacitors that had oil in them actually had a little tube that stuck out. That's where the oil was filled, and then it had the wire lead attached and was soldered to close up the capacitor. So that's a very different type of capacitor, a very old style of capacitor. But they do have a similar look with that little tube sticking out. Also, some good news is that I found the correct manual for this Fluke 8125A. So in the part 1 video, I mentioned that I didn't have the correct manual and I was relying on the 8120A user manual, tech manual. It has all the schematics and everything in it. Well, I did manage to find the correct 8125A service manual and user manual. It has all the schematics and all the tech info in it. And what's very nice about that is it has the circuit board drawing and all the component locations and everything that are correct for this 8125A, plus the differences that this 8125A has, like the heater circuits for heating it in cold weather and things like that that are unique to this model. Also, the manual mentions that this 8125A is basically the same as an 8110A, which was a commercial version, just a typical produced digital multimeter at that time. It was not a military meter, where this 8125A was intended for the military's use. So the 8125A is based on the 8110A. And in fact, the manual for the 8125A contains a copy of the 8110A manual as well. They're that similar. So it's good to have that for the troubleshooting and again, the component layout and all the details that are unique to this particular model. So all the new capacitors have now been installed, but unfortunately the project has been delayed and the troubleshooting took a bit of a detour because of a mistake that I made. So here's what happened. After I installed all the new capacitors, I powered up the instrument and the Nixie tubes lit up, and I thought, great, that looks promising. So I wanted to do a quick test on the instrument just to make sure everything was looking okay, and I noticed right away that the ring counter circuit was still unstable, just like it was before and everything that I showed you in that part 1 video. So touching that test link jumper stabilizes the ring counter, and that hadn't changed. So I did that, the ring counter became very stable, and I put some DC voltage, AC voltage, a couple test resistors, and everything was looking very, very good at that point. So then I thought, well, it wouldn't be a bad idea just to check the power supply rail voltages in the instrument. So I went around and was checking some of the voltages, and everything looked good. I used the oscilloscope and I was just checking for any excessive ripple. Everything looks spot on. So great, no problems. I could continue with the troubleshooting on the ring counter. The last voltage that I checked, the positive 200 volts going to the Nixie tubes, and my test probe slipped. Oh, not good. So it slipped from the positive 200 volts on the filter capacitor down to trace on the board right next to the the filter capacitor. Now, I was really kicking myself when this happened, in big part because I was using the wrong probes. I was using the probes that I have on my multimeter just for general purpose, and you may have seen that I use a smaller type of probe with a very sharp needle point when I'm testing on some of the more delicate components or small traces and so forth. And I like those probes because they are so sharp, they basically kind of dig into the solder and they help you from not slipping. You know, they'll keep the probe in place and you can very precisely get into small areas. Well, I was using the larger probes and they just don't grab the same way on the traces, and it slipped and it caused a short circuit. So again, 200 volts down to one of the other traces. Well, when that happened, there was a snap and the instrument shut off, but then it turned back on. I mean, when I say shut off, the display went blank, but it turned back on, but was flickering and all kinds of random numbers and everything. So I quickly shut the instrument off. And I started looking around. I didn't see anything. I turned it, you know, that looked like overheated or anything like that. But I turned the instrument back on, and immediately I noticed that one of the integrated circuits was getting extremely hot, and the display was just complete gibberish. Now, the flickering that you see on the display right now is just the camera, shutter speed not cooperating with the refresh rate on the display, because to my eye, it's very stable at this point. So obviously there was going to be some troubleshooting to figure out exactly what I destroyed with this probe slipping. So I'll zoom you in on the circuit board and I'll show you where it slipped, and then we'll go over to the schematic and I'll show you what happened electrically, and I'll show you the components that were damaged. At this point, all of the components have been replaced, and I'm back on track to continue with the troubleshooting in that ring counter. So of course the instrument is not powered up right now, and this is the test probe I was using when I slipped and caused that short circuit. So this is just a standard issue test probe that comes with the digital multimeter, but it's definitely much larger than the type of test probe I would normally use when working on a circuit board like this. And again, that point is not as needle sharp as the type of test probe that I should have been using. Now, incidentally, I have this type of a test probe right here where you can turn this collar. It makes that little sleeve move out right here. So it's a very good idea, and it can prevent short circuits if this portion of the test probe comes in contact with an adjacent component. But yeah, I wasn't using that either. So just got in too much of a rush and the wrong tool for the job. So definitely made myself a lot of extra work. But going back to the circuit board right here, when I was taking the measurement, this is the 200 volt capacitor. It's been changed. This is the positive side over here. You can see a little positive mark on the board right there. Now the negative test probe was over in that far corner of the board on test point number 1. That's just a circuit common for all the power supplies. So again, the negative was clipped onto test point number 1, and I came in with this test probe right here. And you know, on the end of the test probe, it has like a little bit of a notch in the end right there, and I kind of hooked that over the end of the wire right there in this capacitor. You know, you're just touching on that lead, so if you kind of go over, you can kind of feel it kind of catch on the test probe end. Well, I did that, or I thought I did, and it, you know, was touching right there, but unfortunately it went right like that, right off that edge, that, you know, where it makes the 90-degree bend and goes down to the board. Well, it slipped right off of that, and this trace right here, so you see this resistor right here, it's a 10K ohm resistor, and we have a transistor right here. So this trace right here, this was touching this corner of this lead, and it went right down to the board because it slipped and it didn't catch on the, you know, on the wire right here on the component lead, and it slipped right down to that trace, and it made a contact, you know, and just bridged right across that point right there. And when it did that, it made a spark, and it made a snapping sound, of course, and it basically just discharged this capacitor. This 200 volt power supply is fairly low current, so when it discharged, it wasn't, you know, continuously putting, you know, a constant 200 volts out, and I'm sure that saved a lot of other components because it basically just discharged this capacitor very quickly. But nonetheless, it did cause some damage to a number of components. So let me move you over to the schematic and I'll show you exactly what happened. Since I knew exactly where the test probe had slipped and touched on the circuit board, when I looked at the schematic, I quickly realized it was this point right here where the test probe had touched. So essentially it put 200 volts on the circuit right here, and of course it was never meant for that kind of voltage at that point. So the 200 volts on the capacitor wants to return back to circuit common because that's where the other side of the capacitor is connected. So if you look at the schematic, you can see right here this triangle symbol right here, another symbol right here. So those are all the circuit commons in the power supply. It's not the same thing as earth ground or chassis ground. Again, it's just a common point on the power supply. But because the 200 volts wants to return to that circuit common, any components that have a direct or somewhat indirect connection to the circuit common were certainly prone to being damaged by that 200 volts because, you know, the 200 volts would essentially just arc through internally in the component and make its way back to that common point in the power supply. So starting right here, if we go this way, we have this transistor Q66. It's acting like a switch to turn on this neon indicator that forms a 1 digit on the display. And if we come up here, there's a current limiting resistor, and then there's the 200 volt power supply rail. Well, the 200 volts here wouldn't want to go back up to this 200 volts. It's the same point. You know, the 200 volts here is what I ended up shorting to this point right here. So this transistor survived, no damage to that component. And this resistor right here is a 10K resistor, and there was no damage to that resistor. Again, the 200 volts discharged very quickly from that capacitor, but the 200 volt supply is a very low current supply, so it wasn't able to hold the 200 volts up very long. So components like resistors were not damaged by overheating, things like that. But going back this way, you can see this is a logic NAND gate. So there's 3 of these. They're all in the same package. It's integrated circuit number 3, or A3, which is a triple 3-input NAND gate. And so you can see one right here, another one here, and then there's another one on the other schematic that is part of the power supply circuit. So when this integrated circuit is in a socket, and when I pulled it out of the socket to test it, it was testing bad. All of the pins on that chip were basically shorted together internally. So it just melted that chip down inside. So that's not a good thing because that 200 volts could then pass through this and continue on to some additional circuitry, or it appeared that it could possibly do so. Now, this chip has a connection to the circuit common, of course the 5-volt rail as well, to get its power. So that 200 volts could certainly have discharged through this NAND gate and gone to ground, but continuing on the other side, we have a 2.2 k ohm resistor, and this goes to some transformer windings. Those components were perfectly fine. But if we go over here on this line right here, it comes up, goes to this FET right here, which is acting like a switch, comes up here, and it goes to this counter, integrated circuit A4, and over here to the decoder driver, which is A5, or integrated circuit number 5. So I tested A4, it's in a socket, I just pulled it out, and it also tested bad. So a number of its pins were all shorted together, or had very low resistances. So, you know, that's 2 components now. The NAND gate is defective, and the counter is defective as well. And that's a binary counter. So the decoder driver actually survived, thankfully. So I was able to test it by having A4 and A3 removed and then powering up the multimeter and then using the internal 5-volt supply and just applying that 5 volts to these inputs right here that go to this decoder driver, which is basically a binary coded decimal, and it drives the 10 outputs that go to the Nixie tube, so digits 0 through 9. And it worked okay. It was able to decode the inputs and drive the Nixie tubes the right way. So thankfully, there was no damage on that particular part. But going back here, this additional circuitry, again, the FET survived. That was a very good news. This NAND gate right here was all shorted out. Just internally, that chip was completely defective. So, you know, it was pulling all of the lines down, you know, all to a common point, and it was completely destroyed. But I was not seeing any other problems on other components until I got into this area right here, and I started checking these transistors and discovered that Q45 was defective and had been damaged. So thankfully the other transistors were okay. But Q45, if we look, the base goes to ground. If we follow back this way on the emitter, we have a diode comes over here, down, and look where we're right back to this NAND gate that was defective. So the 200 volts just came through here, shorted out this NAND gate, came over this way, came up over here, anode to cathode, over this way, just went through from emitter to base. It couldn't withstand that voltage, and then just went to the circuit common. So not surprising that this component was damaged as well. So the problem with Q45 is that Q45 is a 2N3904, which is an NPN transistor, and there's several of them in this circuit over here, and they all appear to be matched. They all have a red and green stripe. So I really wanted to keep them as a matched set, and it seemed like that would be a good idea. And I discovered that this transistor right here, Q84, was also a 2N3904 and had the same 2 colored stripes on it. Now this is just being used as a switch, but it's unrelated to the switching over here, and I didn't think it needed to be matched, you know, closely to this group of transistors given what it's doing. So I went ahead and moved this transistor over to Q45's position, which then kept an original set, you know, that appeared to be closely matched. And Q84, I was able to replace it with a 2N3904 that I had on hand that only had the red stripe on it. It did not have the 2 colored stripes on it. I tested it, and its gain, or the HFE of that transistor that I had as a spare, brand new, was a little bit higher than the others that I was testing over here, but that shouldn't be a problem. Again, this is just being used as a switch. It basically forms an OR circuit right here because you have a logic signal coming into the base right here, and when it switches this transistor on, it makes this 5 volts come over here, comes up to this point and goes this way, activates this switch, or the input can come right here through this diode and activate this switch. So it's basically selecting this, or both could be high at the same time. It would still cause a high over here. So just a logic OR. So having plenty of gain on this transistor is not a problem. It just ensures that it saturates fully. So again, having a little bit higher HFE value than the original was not going to be a concern. So ultimately, 3 components ended up being damaged. After extensive testing on other components, I was not seeing anything else that looked to be damaged. So I think by applying 200 volts accidentally to this point right here to only have 3 components that ended up being damaged, ended up being pretty lucky, I suppose. So right here are the components that were damaged. I have to find this little sheet of paper right here. So integrated circuit 3, integrated circuit number 4, and then Q45. So again, these have all been replaced. I was able to find the new old stock on these 2 integrated circuits, and then the replacement transistor I had on hand here, which was old stock as well, and brand new. So all of that's been installed, and as you already saw, the multimeter powers up and is back to the point where it was previously before I caused this damage. So now I can continue with the troubleshooting and figure out exactly what's going on with that ring counter. All right, so after quite a bit of experimentation and testing on the ring counter circuit, I believe I know how to solve the problem that this instrument is having. So I have this set up right now with these test leads connected to this 40K ohm resistor, and I haven't done anything to the ring counter circuit at this point. So I'm going to turn the instrument on, and you'll see that it's acting just the way it always has. So it's very unstable, and the display is jumping around. And I want to show that just because of the repairs that I've done, because of the damage that I caused with that probe that slipped and all of the new capacitors that I installed. None of that had any effect on the instability of that ring counter circuit. So I'll turn this on. Okay, so you can see the display, how it's just jumping around on the numbers just like before. And it's in the resistance mode right now. So what it should be doing, of course, is displaying something very close to 40K ohms on the display. And if I take this test lead like before, I won't touch anything on this side. And if I take this other test lead end and touch it to this test link jumper number 1 right here, so there it goes. So now it's locked in, very stable reading, so 39.75 K ohms. Now the instrument has not been calibrated, but that's reading very, very close. And the display flicker that you see right now on the camera is not apparent to my eye. It's very stable. So what I believe is the solution to this problem is to add a capacitor in the ring counter circuit, because effectively touching that jumper wire is adding capacitance on test link number 1. So if you take a look at the schematic right here, so here's test link number 1, and when I touch that point, the multimeter becomes very stable. So really what that's doing, if we follow this down here, that's going on the collector of Q20 right here, and then the emitter is going to the circuit common. I mentioned those little triangle symbols are the circuit common in the power supply. So if I put a capacitor, a very light value capacitor, between the collector and emitter of this transistor, the instrument starts to function correctly. And I've already tested that. It does work. And how small of a capacitor? Well, I found that 33 picofarad is all that it needs to stabilize it. Now, I have no idea why the ring counter circuit insists on being so unstable until that capacitance is there. I've tested every component. I cannot find any semiconductors that are faulty, the transistors. Everything is testing perfect. All the capacitors are still testing perfect that are in the ring counter circuit. And then the circuits that the ring counter drives, because it controls many other circuits in the instrument, have no issues whatsoever. So adding this capacitor stabilizes the ring counter, and the good news is it has no ill effects about leaving that capacitance in the circuit. So it remains very stable. It doesn't affect the accuracy of the instrument or anything else. The waveform on the ring counter also looks very, very stable, and no issues with that capacitance remaining in the circuit. So here's the capacitors that I have right here. So these are 33 picofarad, right there. Very small. So these are multi-layer ceramic capacitors, and they're rated 50 volts, and they're the C0G type, 5% rated tolerance. So they're very, very stable with regard to temperature and applied voltage. So it will remain at that 33 picofarad value, or very, very close to that value, once it's in the circuit. So I'm going to go ahead and get one of those little capacitors permanently installed. I previously had just clipped it in very, very carefully into the circuit and found that it did solve the problem. So I'm going to go ahead and solder it in permanently. I'm going to make the leads extremely short, and I'm going to solder it right across the collector to emitter on that one transistor that I just showed you. But I'll do it on the back side of the board, and it'll be very easy to put it right across the traces on the board. And once it's soldered in there, let's see if it actually solves the problem permanently, because when I turn the instrument on, it should immediately lock in and display the correct value. It shouldn't be jumping around. So I'm going to do that next. Now, I just want to add that when you're doing a repair on a circuit or something like this, adding a component in, you want to be careful that you're not just masking another problem. So let's say you had a faulty resistor that had drifted. You wouldn't want to necessarily parallel it with another resistor trying to fix the problem. Or let's say you had a faulty capacitor. You would never want to parallel the capacitor with another capacitor trying to, increase capacitance or something like that. That's just a disaster waiting to happen because the faulty component is still in the circuit. In this case, I don't believe there's any components that are faulty, and it's just perhaps a component has aged to some degree. There may be a transistor that has maybe some leakage current or something going on that isn't supposed to be there, that's maybe a little excessive. It's not showing up when I test them though, so I'm not seeing any components that have failed. And as you can see, the instrument locks in and works perfectly fine when it once it's in a stable state. So I don't believe that this is really masking, over a faulty component. And 33 picofarad is an extremely small value of capacitance. That's very, very small. So I'd be worried. I wouldn't want to be doing this if I was hanging, a 10 microfarad capacitor into the circuit or something like that. That could have, really bad effects on how the circuit functions, or would really be masking maybe another problem. But in this case, I believe it's, the solution that should work. And of course, this instrument ultimately is going to remain on my bench, and I'm going to use it. And if the problem reoccurs once I do this modification, I can certainly open up the instrument and revisit this in a future video and take a look at it if this doesn't ultimately solve the problem in the long term. But I think it will. I think this is going to be the fix for the instrument. So I'm going to go ahead and get that capacitor soldered in, and let's see what the result and how it looks. All right, so the 33 picofarad capacitor is now installed. You can see it right there. So it's across the collector to emitter on Q20. And this zip tie is just holding this cable out of the way because, of course, the cable wants to pass right over the top of where I had to solder the capacitor. So let's see if the instrument is working the way that it's supposed to. All right, let's see if the 8125A is working the way that it's supposed to. So like before, it's plugged into my isolation transformer for the line power, and these test leads right here are going over to that 40 k ohm resistor. So let's see what happens. Turn this on. Hey, look at that. 39.75 k ohms. It locked right in. No problems. So again, the display is flickering on the camera, but those Nixie tubes are very, very stable to my eye. So excellent. It looks like it's working the way that it's supposed to now. I'm really happy with that result. So what I need to do is calibrate the instrument now. So I'm going to put all the shielding back in place and then work through the calibration procedure. Now, I don't think it'll be all that interesting in doing the calibration procedure. As I work through that, if something really stands out or seems kind of interesting, or if I run into any problems, I'll of course include that in the video. So I'll get started on all of that next, and just kind of see how that plays out as far as the calibration process. Because again, it's basically just applying voltages, resistances to the digital multimeter and making the adjustments that are on the circuit board. So really not that interesting. But again, any problems that come up, I'll definitely include it in the video. All right, so I installed the metal shields in the Fluke 8125A, and then I completed the calibration procedure just as it's listed in the service manual. And I have to say I'm extremely happy with the results. So this multimeter is looking spot on. It's very, very accurate. So I'll go through a couple measurement examples and you can see how things turned out. Now, the only thing that I couldn't do that's listed in the calibration procedure is to verify the accuracy up to 1,000 volts AC at up to 20 kilohertz, because I just don't have a power supply that has that capability. But I was able to measure up to several hundred volts on the 1,000 volt range at up to 10 kilohertz, and the multimeter worked perfectly fine. Now, in the volts DC range, I was able to measure up to 1,000 volts with no problems. Now, obviously, when you're doing this calibration, you want to have the metal shields installed first and then do the calibration, because if you calibrate the instrument and then put the shields in place, it could throw the calibration off. Now, this top shield right here and then the shield that's on the bottom are electrically floating or isolated from the frame or chassis of the instrument, so it's also important that those not be shorting out against the side rails or something like that. And there's some nylon standoffs that hold everything in place and keep it isolated and insulated. So when you're doing the calibration and you reach through from the bottom, there's little holes, and that's how you get to the potentiometers for the calibration. When you reach through those holes, you have to use an insulated screwdriver because you wouldn't want to short out that bottom shield. Now, there's also a panel on the bottom of the instrument that holds the power resistors for heating the instrument in very cold weather, but that metal panel is not electrically floating because it's tied to the front panel. Now, I noticed that in doing the calibration, every single calibration point needed some touching up. Some were a ways off, but none of them were, wildly out of spec. But again, everything did need some touching up. So I think that sticker that we saw on the front panel that said that the instrument had been calibrated probably many, many years ago, I think it was accurate. It probably had been calibrated, but it's interesting that it had such physical damage, with the bent metal and the other issues going on, but yet still seemed to be calibrated, and it was rather close. I mean, we saw initially when it started working that it was taking some readings that weren't, way out of spec. So, it's pretty cool to see this Fluke 8125A sitting here working like factory new, given the condition that it started with, and it really shows, just how tough these instruments were built. So after I show you a couple measurements here, I'll zoom you in a little bit closer, and you can see the metal shields on the top and bottom of the instrument and how everything fits together. So to do the calibration, the test equipment that I used is my EDC model 522RA7, which is a DC calibrator, my Fluke 382A, which is a voltage and current calibrator, the Bellman KBT 100-436C, which is an AC power source, my Bertan 205A-01R, which is a high voltage DC supply, the BK Precision 4062B, which is a function generator, and that's needed for the very low voltage AC ranges, and of course a handful of various resistors. And everything is measured against the Keysight 34465A digital multimeter that you see sitting here. So that digital multimeter is under a factory calibration, so it's very, very accurate. And so basically everything is just measured against that multimeter. So for example, some of the resistors that I have, they're not necessarily precision resistors. Like I think the 1 megohm resistor that I used is a 5% tolerance. So it's not spot on 1 meg, but whatever its value is that it measured on the Keysight, that's what the 8125A was then calibrated to end up showing. So basically the 8125A has been calibrated against the Keysight and is measuring exactly the same readouts as what the Keysight shows. All right, so you can see right now on the display it's showing 1 volt DC, and it's spot on 1 volt. We have 1 volt over there, so no problems. So if I go to the 10 volt range right here, of course it's still showing 1 volt, and I'll go over here to the DC calibrator and I'll change this over to the 10 volt range. So that's 10 volts right there. It'll have to settle in a little bit. Takes a little bit of time here to dial in. Right there. So right at 10 volts, and no problems, sitting right at 10 volts there. And if I go to the 100 volt range, and then I step this up here to 100 volts, it needs to settle in. So right there, looking very close, right on 100 volts, and no problems. And I can go to the 1,000 volt range. I'm not going to connect the 1,000 volt power supply, but it works perfectly fine on the 1,000 volt range as well. So let me move things over to the BK Precision function generator, and I'll show you a couple of measurements on the AC volt ranges at a couple different frequencies. All right, so there it is sitting at 1 volt AC. So we're at 1.000 and then 7 volts AC. And it's basically within one count of what the Keysight is showing over there. So that's down into the hundreds of microvolts over there. So very accurate, no problems there. And that's 1 volt at 1 kilohertz. So I'll change that frequency now. If we go over here to frequency, and I'll go to 60 hertz. So 1 volt at 60 hertz, again, very close, basically within agreement over there to the Keysight within a couple counts. And if I go to 20 kilohertz, so that's 1 volt at 20 kilohertz. No problems there, spot on. I mean, it's in exact agreement with the Keysight. So if I go to the 10 volt range, and I'll just step this up here, go amplitude. So that's 7 volts RMS, or it should be very close to that value. And you can see within about 1 count from the Keysight. So, and that's still at 20 kilohertz, so no problems there. And I'll change the frequency. Let's go here down to, say, 60 hertz. So that settled in very close to 7 volts. Just a few counts high, but that's only a few millivolts off. So no issues with that. It's right within the tolerance and specs that are given for the 8125A. Let me connect the test leads over to my isolation transformer. We'll try a higher voltage AC range. All right, and there's the reading off of my isolation transformer. So I'm sitting 119.99, so that's right at 120 volts. And the Keysight is showing 120 volts. So no problems whatsoever. All right, now I have a precision 4.99 k ohm resistor connected to the Fluke 8125A, and you can see the display, 4.99 k ohms, so the reading is spot on. So now let's see what the Keysight shows, see if the readings agree. No problems, 4.9898. Very, very close, so no issues there. All right, I now have a 5 megohm resistor connected to the Fluke 8125A, and this is in the 10 megohm setting, so in 10 megohms, these range switches are no longer used. So you can see when I bring my hand near this, it causes the numbers to change a little bit, so the reading fluctuates slightly, and then it settles back down. And I noticed that when I was doing the calibration on this 10 megohm setting that it's very sensitive to the test leads, being near anything or moving. So it's just very, very sensitive. But again, a 5 megohm resistor, and it's showing 4.99 megohms. So very, very close to the expected value. Now I'll move that resistor over to the Keysight, and let's see what the measured value shows on that meter, see if it's in agreement. So 4.996 megohms. So, a few counts off, but very, very close. No problems whatsoever. So here's a look at how the shields fit into the instrument. So you can see on this top shield there's these 6 screws. So those are just holding the bracket on the inside of that shield where the battery would be installed. But if we look along the side right here, so you have this long side rail, and then there's this gap, and then the shield. And then the same thing over here, so you have the shield, there's a gap right here, and then this side rail. So there are nylon insulators that are part of the shield, and then there's a screw right here, and another one right there and over here. So those screws go into the nylon insulators, and those nylon insulators create this space that's needed and the insulation. If I turn this, so you can see a very close fit along the components. The shield goes down to the circuit board. It just goes right above the traces and just clears all those components. And the same thing on the back edge right here. So very close fit down in there. And then in this corner right here, you can see there's a yellow wire that comes up and it attaches right there. So that's the only electrical connection that this shield has to the circuitry. And again, that's not a ground connection on the shield. That's a floating connection, within the circuitry of the multimeter. And if I turn this around like so, so on the bottom panel right here, so these are the resistors for the heating and cold weather. So this panel is at earth ground potential. It's connected to the front panel. There's an L bracket right there. And this input filter where the AC line comes in has an earth ground connection through the cord. So all of this again is at earth ground potential. Now this bracket right here, it's like an L bracket. It goes from this front panel down to this front edge of this panel. And that bracket was bent. Again, I have no idea how that ended up getting bent. Again, a number of areas in the metal on this instrument had been bent. So very, very rough handling, but that was able to be straightened out. So it fits correctly now. And if you look right here, there's two switches. So one of these is a thermal switch that controls these heaters, and the other one is a lockout so that if there's extremely cold weather, it prevents the instrument from being turned on until it actually reaches the correct operating temperature. And this panel right here where it comes up underneath these fuse holders is a very close fit, and there's a metal ring, on each fuse holder where the wiring attaches, a very, very close fit under there, and there's an insulated piece that's adhered to this panel, another insulated piece right here, so it's AC line coming in right there. But everything clears correctly, very, very close fit. So if you are working on one of these instruments, make sure that nothing shorts out, in this area up here. And turn right here, you can see. So this is the shield that's electrically isolated right here. So this shield is mounted to standoffs that are on the circuit board, and then there are nylon spacers between this shield and then this bottom panel. And same thing again if I turn it back over this way, you can kind of see down in there. So the spaces between the different pieces. And the standoffs that were on the circuit board that this shield is mounted to, two of them had cracked solders. So they're attached to the circuit board, kind of like how a rivet would be attached, but then they're also soldered for a good electrical connection. And again, two of those solders were broken, so I touched that up as well. In this back corner right here, you can see there's a green ground wire. It's bonded on right there, rivet and a terminal right there. So again, this is at earth ground. And I mentioned the calibration points, and you can see all of them all over right here. They're all labeled as to what they do. So the troubleshooting, repairs, and restoration on this Fluke 8125A digital multimeter are now complete. I'm very happy how the project turned out. The digital multimeter is extremely accurate, and it has a very neat retro look when it's in operation, so definitely looking forward to putting it to use on the bench. So I hope you enjoyed following along on this project, and if you did, you can let me know by giving the video a thumbs up. And if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. Lots and lots of projects in the queue. You won't want to miss any of that. Don't forget to tap the bell symbol to be notified when I do post a new video. All right, until next time, take care, and as always, thanks for watching. Goodbye for now.